So today we want to start talking about lenses and how lenses can form images and how they bend light rays. So we have two different types of lenses. Some books call them convex and concave. Your book calls them positive and negative. Okay, so what is a positive lens and what is a negative lens? So a positive lens is a lens that viewed from the side looks something like this. So this is a positive. And a negative lens is something that might look like this. That's not very good. Let's lengthen that up. So a negative lens is something that might look a little bit like that. Alright, so that's a negative lens. And most books start talking about the positive lens first. Alright, so first of all, where are positive lenses found? Well, they're found in most optical systems, most systems that use a lens system. One of them will be positive. But also your typical magnifying glasses, your everyday magnifying glasses, are going to be of a positive type. All right, so let's start talking about a lens. And every lens, if the lens is completely symmetric, so this is a perfect positive lens. We're not talking about a lens that's composed of two different types, but a perfect lens will be symmetric about the axis, right around the middle. So it will be symmetric around the middle, and each lens has what's called a focal point. Okay, so every lens has what's called a focal point. So what is the focal point? Well, if you're looking at your lens and looking at light coming from a very distant light source, right? If you look at light coming from a very distant light source, then the light rays coming into the lens from that light source can be thought of as parallel rays, right? So whatever the source of these light rays is, if they're far away, they'll be coming in at essentially parallel planes. Now what happens to the light rays when they hit the lens? Well, because the glass has a different index of refraction than air, it will bend due to the law of refraction. So the top beam will bend down this way. This beam will bend a little bit less. This beam will go straight through. This beam will get bent upward a little bit, and this beam will get bent upward quite a bit. And where all of these rays meet is called the focal point. Okay. Some people denote it with big F, so we'll denote it with capital F, as your book does. So that's the focal point F. All right. Now, a positive lens, a perfect positive lens, has a focal point on either side of the lens, and they're both going to be the same distance away from this central axis through the lens. All right, and that is what we call the focal length F, lowercase f. So capital F is the focal point, and little f is the focal length, which is just the distance from the axis to the focal point. All right. So capital F is a physical point in space. And little f is a length. All right. Okay. So now how do we actually determine if I'm looking at an object, or if I have an object that's shining light rays through the lens, where will the image of that object be formed? Okay, so this is the question, And this has to do with what's called the thin lens equation, all right? Or sometimes it's just called the lens equation. And it says this, right? 1 over O plus 1 over I equals 1 over F. Now what exactly does that mean? O, here's going to be the distance of the object to the lens, and I is going to be the distance of the object, of the image to the lens. All right, so I is the distance of the image from the lens. So let's actually set up an object. Ideally, if we have a lens, what we want to do is draw an axis right through the middle. All right, now that's not right through the middle, but it's close enough for government work. All right, so imagine that I have a lens here, and here's one focal point, and here's the other focal point. Now imagine that I have a candle. And it's burning, giving off light, and smoke is coming up off the candle. All right, and I want to view the candle through the lens. Right, where is the candle's image going to be located? In other words, where do I have to put my eye from the lens to see an image of a clear image of the candle? So the way to do this is what we call ray tracing. Okay, ray tracing. And what we do is we choose 3 rays from the candle. All right, and first note that the distance from the focal point to the axis will be denoted as little f. The distance from the object to the axis will be our O, and then over here somewhere, wherever the image is, that will be I. Okay, so that ties in with the equation. All right. Okay, so let's actually see if we can set up a slightly better lens here. Let me make that focal point a little bit further back. That's good. All right, so there's our focal points. And again, here's our candle. All right, so what I want to do is draw 3 lines, okay? And the first line, or 3 rays coming out of the candle that might go through the lens. So the first ray I'm going to draw is going to be parallel with this axis. All right, so it's going to come in straight like this, and then when it hits the candle, we know that it's going to get bent through the focal point like this. A second ray I can trace is going to go through the center of the lens, and a ray that goes through the center of the lens will go undeflected. So it'll go like that. And then a third ray that I can draw, if my object is beyond the focal point, right, I can draw a ray that goes through the focal point, hits the lens, and then the ray that hits the lens in this manner will come out parallel to the axis. Right? So our diagram looks something like this. And this isn't a great diagram because they don't all 3 match up, but where they all three should meet at the exact same point. So my sketch is off just a little bit, all right, but they all should meet at the same point. I think my focal length on the right side here is a little off. But the point is, okay, they all three will converge at a point over here somewhere. And this distance now is our image distance. Okay? So, if I know the focal length f, and I know the object distance O, I can compute the image distance I that it will be from the lens, and in this case it will be on the opposite side of the lens. All right? So let's do a quick example. Let's imagine that the focal length here is 10 centimeters, and let's say that the object is 15 centimeters from the lens, and I want to know how far the image is away from the lens. All right? So we can plug all of this into our equation. 1 over O plus 1 over I is equal to 1 over F. All right? Now, remember that I is what I'm solving for. So let's solve it algebraically first. So 1 over I is going to equal 1 over F minus 1 over O. And what I can do now is multiply this fraction by O over O, multiply this fraction by F over F, and this will give me common denominators. So now I have O over FO minus F over FO, right? So this is still 1 over I. So this is equal to O minus F over the product of F times O. Okay? So now, let's go back and review what those values are. So O is 15 centimeters and F is 10. So O is 15, F is 10. So what's I going to be? All right. So if I have 1 over I equals O minus F over O times F, which is what we got right here. Now I can take the reciprocal of both sides, or in other words, just flip them over. So I is going to be equal to OF over O minus F. Whoop. So this is going to equal 15 centimeters times 10 centimeters divided by 15 centimeters minus 5, or minus 10. I'm jumping the gun just a little bit. Minus 10 centimeters. All right? And so, this is going to be 150 square centimeters divided by 5, or equal to 30 centimeters. So in this case, in this drawing, the image is actually going to be twice the distance of the object. All right? So the image will be twice the distance of the object, but that's not always necessarily the case. Okay? They won't always work out like that. Okay, so that's a quick example. And now, let me talk a little bit about the difference between what's known as a virtual image and a real image. Okay, so a real image is formed when the light rays physically converge, as in the previous example. Virtual images, the light rays don't converge. So at this point you might be saying, where in the world would we see virtual images? After all, the previous ray diagram, all of these guys converged. In which case, would they not do that? Well, let's examine a situation in which we have a positive lens, and I'll draw it a little off to the side here. All right, and here's our axis. And let's make this positive lens have a pretty long focal length, so I'll give him a focal point here. What happens if we actually put our candle inside here? All right, what happens to the ray diagram in this case? Well, we can do our three traces again, right? So remember that if I draw a line parallel to the lens, then that ray will go through the focal length at the other end. So it'll go somewhere out here maybe, right? So that ray will go through the lens and then get deflected through the focal length. And again, I can also have a ray that will go up to the top of the lens like this, and if I extend this ray backwards, right, it will go through the focal length that way. So this particular light ray, well, part of it's going this way, and if I have another component emitting exactly opposite, it will go through the focal length this way, right? And also, I can have a ray that, remember, goes through the center. And so it will go undeflected through the center. Now look at what all three of these rays are doing. And by the way, this ray will come out parallel. So on this side of the lens, in this region, the rays are diverging. They're not going to converge. So they can't form an image on this side of the lens. So what can we do? What we do is extend the rays on this side of the lens backward. Right? So in other words, this ray is going to get extended back this way. This ray is going to get extended back this way. And this ray is going to get extended back this way. And again, the sketch is off just a little bit. It's not perfect. But the rays are going to converge in this area. Right? And in this case, the image is going to be here. And again, this was the object distance here, and this was the focal length f. And this will still obey the lens equation. You solve it just like we did before, only with the new values, whatever your O and your f might be. Now there's one more thing to notice, right? Remember back a few slides ago, here the image is probably going to be a little bit smaller than the object. Alright, so the image is going to be a little bit smaller than the object, whereas here the image is going to be a little bit bigger. Right? So here's where you get your magnifying glass. Here's where you get your magnifying glass. If you hold your magnifying glass up to a page such that the page is within the focal length, then the words will appear larger. All right? So that's what's going on. Okay, so that's enough about the positive lens. Next time we'll look at the negative lens and we'll do some examples with that, and then we'll start talking about mirrors.